Welcome to this lesson on exponential transformations. By the end of this lesson, you'll be able to graph an exponential function, you'll be able to translate the parent function of an exponential function, and you'll be able to explain which each part of the equation represents in a graph given an exponential equation. All right, so most of us, when we think of transformations, this is what we think of. But this is not what we mean by a transformation in math. Here you see cars moving vertically up and down and horizontally left and right. In mathematics, we call this type of transformation a translation. So when you take something and you move it up or down or left or right, but you don't spin it in any way, then that's just a simple translation. We're not changing the shape of those vehicles. Now check out this triangle here. It is both spinning and changing size. The spinning part is called a rotation. Right? And the changing size part is called the dilation. So those are another types of transformations that we can do in math. Today we're specifically going to concentrate on the center one here. We're going to be taking an exponential equation and we're going to be translating it, shifting it up or down or left or right. We're also going to talk about what creates the change in size. All right, so let's talk more about what an exponential function is. To the right here, you can see the exponential parent function, y equals x to the second power, right? We've already talked about the fact that for an exponential function, the exponent must be in the variable. There's a few other definitions as well. Notice here's our general form for an exponential function, y equals a times b raised to the x. A cannot be 0. B has to be a number greater than 0. And b cannot equal 1. We're going to investigate each of every single one of these claims here and why it must be the case. All right, so here's our exponential basic function, right? It's always in this form where a and b are numbers, right? And the b is referred to as the base of this exponential function because it's acting as the base on the variable x. So our general form here is simple enough. All right, the general shape of our graph is determined by the fact that that variable is in the exponent. That's what makes it exponential. That's what gives it that increasing at an increasing rate, that picture you saw on the last slide, or decreasing at a decreasing rate, which we'll see that as well. But let's talk more about our general form here. Let's ask, what does the role A play and what does the role that B play? Well, let's take a look. All right, so consider our general function here. What do you think will happen if we fix A, but let B become a larger positive number? That is, make B a number larger than 1. What do we think is going to happen? Well, let's check it out. Let's go to www.desmos.com and let's play with that. All right, so in this equation here, notice that I typed right in our general form of our equation here, then I set up sliders for A and B. I'm going to fix A at 1. And we're going to go ahead and let B vary between 1 and 10, a positive number. So I'm going to go ahead and play that animation for you, so you can see what it's doing to the graph. All right, so now notice that as B is becoming larger and larger, like here it is at 9, right? It just increases very sharply. Remember, this is the base of our exponential function here. So if I make a base and a larger number and I raise it to numbers, it's going to rise quicker. So you can see that it's shooting up even quicker than if I let it be, say, 8 or 6 or 5. Notice here when it's at 3, it becomes a little bit wider. So it's still increasing. It's just not increasing as fast. All right, so that's what happens when I let b become a larger number, larger than 1. It gets steeper and steeper. All right, so that's what we saw when b was larger than 1. What do you think will happen if we still fix a? We're going to keep a fixed, but we're going to let b become a fraction, a decimal, a number between 0 and 1. All right, well, let's go to Desmos again and let's see what happens. Let's try it. All right, so I'm still going to fix A, but I'm going to go ahead and change my slider on B here. So now we want it to be a number between 0 and 1. Okay, so we're going to make it between 0 and 1. And we're going to investigate what happens. All right, so now notice when we start out, here's a fraction, all of a sudden now the graph, right, is flipped. It kind of flipped it over the y-axis, didn't it? Instead of increasing at an increasing rate, now we see that it's decreasing at a decreasing rate. So this is what we refer to, as you should have learned in the last unit, right, as exponential decay. So now this exponential function is decaying when I let the base of this exponential function be a fraction, a number between 0 and 1. And notice that as I make that fraction closer and closer to 1, it kind of widens out. It decreases the rate, the change in rate, right? So it's kind of flattening out and becoming wider, stretching it away from the y-axis, all the way until exactly 1. Then we see there that it's a flat line. So as I make B closer and closer to 0, right, as I get it absolutely closer to 0, then you see that it is decreasing at a faster rate. So it's making it the skinnier, if you will, right, closer, squeezing it, compressing it toward the y-axis. All right, so when I have B that's a fraction, when I let that fraction get closer to 1, it makes it wider, but it's still decreasing, right? It's exponential decay. And when I let that value get closer to 0 as a decimal, right, we still have exponential decay. Here, B is 0.1, right, but it's decreasing quicker. Let's go ahead and play that animation out smoothly so you can watch that happen. All right. So we've made B positive, larger than 1, and we saw that we got exponential growth, and that the larger we made B, the faster it increased, kind of the skinnier it got, so to speak. We saw now what happens when B, we made it be a fraction between 0 and 1. Then we got exponential decay, right? It started decreasing. The closer that number was to 1, the wider that decrease was, or the slower that it happened. And the closer that I got that value B to 0, like say when it was 0.1, right, it was decreasing sharply, right? And so decreasing at a faster rate. Now, what do you think will happen if we let B be a negative number? So let's see what happens, because if you recall on my very first slide, we said that B cannot be a negative number, right? That it had to be greater than 0. So, and also it had to be strictly greater than 0, couldn't even equal 0. So let's talk about first what happens when we let B be 0. Then I want you to think about what will happen if we let B be a negative number, the base be a negative. All right, well, let's go to Desmos again and let's check out. Let's try to do it. All right, so let's go ahead and let B equal to 0. All right, so I'm going to move the slider all the way back, and B is going to be equal 0. Now, it might be hard to see on your screen, but you'll notice that we get a line starting at 0 here and going to the right, a horizontal line. All right, because think about if we take 0 and raise it to some power. All right, we take it to raise 0 to the first power, to the second, to the third, to the fourth power. Well, then we still get 0. And 0 times anything is still 0. So we just get the function that y is equal to 0. Well, that's a horizontal line at 0. And that's why we're just seeing this horizontal line here. And that's why we say that b cannot equal 0. Because if b is equal to 0, you see that we don't even get an exponential function anymore. We get the equation of a line. All right, well, let's go ahead and let's see if we can let b be negative. I'm going to go ahead and change the slider values here. Let's just make it go between, let's say, negative 10 and a 0 and see what happens. All right, I'm going to go ahead and play it. Okay, so our slider's playing. I don't see a picture. I see nothing being graphed. Let me just make sure that's not a mistake. I'm going to grab it. I'm going to set b now to some negative value. No graph. I don't see a graph anywhere. What if it's -2? Do I get a graph? No, there's no graph at all. All right, so we'll go back and we'll investigate why we don't see a picture when we let b be a negative number. It was part of our definition, right, that b can't be negative. But let's see mathematically why b cannot be a negative number. We have shown here that we don't get a graph when it's negative, so something's going on. All right, so let's go back and investigate this a little bit more. All right, so let's consider a function where I went ahead and I made the b a negative number. Like in this case, I made it -2. So we get this function y equals -2 raised to the x. All right, so what happens when x is an even number? Let's start there. Remember, so x is our input variable. We can let it be anything we want. Let's see what would happen if I let it be a negative or an even number rather. All right, so like for example, like 2, 4, 6, 8, whatever. Okay, so suppose I put in, I'm going to make a little table here. Suppose here's our x and here's our y. What if I plug in a 2 for the x? What do I get for y? All right, well, I'd get -2 squared, which would be -2 times -2. Okay, well, that would be +4. If I let x be another even number, let's say 4, then I'd be raising it to the 4th power now. So now I have a negative being raised to an even power. And you saw here that ended up being a positive number, right? So whenever I take a negative base here and I raise it to an even power, I'm going to end up with a positive, right? Because a negative times a negative is a positive. Then if I times it by a negative again, it'd be negative, and then back to a positive. In this case, it would be +16. And we could keep doing this, right? I could do this for 6, whatever, and we'd always get these positive outputs here. But I am getting points. So it seems so far that maybe I should see a graph, right, when I graphed it. But we didn't see a graph. Let's keep going. Let's evaluate y. Let's think about now what happens if I let x be an odd number. All right, so let's say I let it be like say if I let it be 1, 3, 5. All right, so let's say if I take this negative base and I raise it to 1, I would get -2 to the 1st power, which would just be -2. If I raised it to the 3rd power, then I'd have -2 times -2 times -2. So a negative times a negative, that would be positive, and then times the negative again would give me back to a negative. So we'd end up back at -8. How about to the 5th power? The same thing. Right? We end up with another. In this case, we'd end up with, let's see, it would go from -32. So now you see what's happening here when we're letting x be an even number and we're letting it be an odd number, when they're whole numbers like this. So what happens here is that it's jumping between positive and negative values. So at 1, it'd be a negative number. And then at 2, it would be a positive number. So our graph would be like jumping back and forth between positive and negatives. Well, why not? Couldn't we have that and have it like connected with a curve in between? The answer is not quite, because think about what happens when we let x be a fraction. Okay, so let's say I let it be 2.3 or 1/2 or 0.8. All right, let's think of the example of 1/2. So that would mean that I have -2 being raised to the 1/2 power. And as some of you might recall, raising something to the 1/2 power means the same as taking its square root. We can write fractional exponents, right, as radicals. So here I'd have the square root then of -2. Oh, but the square root of -2 is undefined, right? When I take the square root of a negative number, it's undefined because that would imply that I can find a number that when I multiply it by its own self is a negative, right? And that doesn't happen because a positive times a positive is a positive, and a negative times a negative is still a positive. So this right here is undefined. So think of any time that I could rewrite an exponent here as a radical, anytime that the index on this radical would be an even number, and I was trying to take the square root or some kind of radical of a negative inside there, I'd get something that was undefined. So that's what happens when we plug it in on Desmos, right? It's going through, it is literally a computer. So it is literally going in and plugging in all the values it can, and then all of a sudden it's going to end up with undefined, undefined, and then that's when it stops. And that's when you don't see a graph. You just see undefined. And so that's how come we have to define the base here to be a positive number. Otherwise, this happens. We end up trying to take the radical or square roots of negative numbers, right? And then we get something that's undefined. All right, so now we've investigated what happens when we change the value of b, right? We've investigated what happens when it's larger than 1, right? We get growth. When it's between 0 and 1, a fraction, we get decay. We saw why it can't be a negative, why it can't be 0. Now let's see what happens if we fix this b value, but we let a change. All right, so let's go ahead and let's check that out on Desmos. So now we're going to fix the b, right? We're going to let a vary. All right, so let's fix the b at 2, so it's in line with our parent function. All right, so now I fix the b at 2, and we're going to go ahead and let a change. We're going to see what happens. Let's start first by exploring what happens when I let a be a positive number. All right, so let's let it step from 0 to 10. And let's investigate what happens. All right, so I want you to look at two things. One, the tail on the left here. Notice how that just keeps approaching 0. We call that a horizontal asymptote. So I notice that when I'm changing the value of a here, my horizontal asymptote does not change. That's one thing I notice. Take a look what's happening with the y-intercept as I change a. It's also changing. So imagine right here, if I stop the graph right here at 3.1, or wherever it stops at, in this case 3.1, and I examine the y-intercept, oh, notice here that the y-intercept is now 0, 3.1. If I let this change so that it is now 4.6, notice how the y-intercept is now at 0, 4.6. So we see that changing the a value does not change our horizontal asymptote, but it does change our y-intercept. And it appears to just be moving the graph up. Notice as it's getting steeper there, it does seem to be increasing at an increasing rate. So just imagine here if we had any value for b to the x, and then I multiplied it by some a value that was positive, right? Is what that would do then is it would multiply the function or the y value by whatever that number was. So imagine our parent function right here when a is 1. So we can see that when a is 1, of course, our graph is crossing at 0, 1. There's our y-intercept. And then notice that if I change that to 2, as we just saw, then now the y-intercept is at 0, 2. So it has the effect of multiplying the y values by 2, or whatever the a happens to be. All right, so it does increase the graph, but it doesn't really change if we play this, right? It doesn't, it's like it's moving that graph up because it's changing every y value. It's multiplying the y values by whatever, but it's not increasing the rate at which it's increasing. Right, so you can kind of see it does make it steeper. It does have the effect of compressing it towards the y-axis. That's because we're multiplying all our output values by whatever the a is. And the larger that number is, of course, the larger we multiply our y values by. All right. So shall we speculate as to what happens when we let a be a negative number? Take a moment to think about it. What do you think is going to happen to this graph if I let a be negative? Well, let's see if you're correct. Let's go graph this on Desmos. All right, so now I'm going to go ahead and let A roam from, let's say, -10 to 0. Let's see what happens on the graph and let it play. So now you notice that as we let A become a larger negative number, two things have happened. Remember, the graph used to be up here, right? Increasing. Now we see that it is going below here, decreasing. In fact, if you really looked, we could see that it flipped it over the y-axis. So just to demonstrate that, let's go ahead and fix A at, let's say, -2. I'm going to fix A at -2. And there's our function. Notice that the y-intercept, 0, -2. Just how it applied when it was positive, right? Let's go ahead and graph the function y equals, let's let A, remember, say what it is. So we're going to change that though to now +2. And we're going to let B be, in this case, since it's 2, I'll leave it at 2. So we don't change that value. Don't want to change both at the same time. And graph that. So take a look at this black function. All right, so it is exactly the same as our red function, except for A in the red function is -2, and it's +2 in our black function. Notice how they are what we call a reflection of each other, and they are reflected over the x-axis. Right, so this point, 0, 2, corresponds to this point, 0, -2 on the red. It's like we flipped it over, and it would fold right on itself if we folded it over that x-axis. All right, so you can think of changing that a value to a negative number has the effect of flipping the exponential function over the x-axis. What we call reflecting it over the x-axis. All right, so our general exponential function is y to the a times b to the x, a times b to the x rather. B is called the base of our function. It has to be larger than, when it's larger than 1, we get a steep increase in the y values as x increases. When it's a fraction, a number between 0 and 1, we get a steep decrease, right, as x increases. So this one's exponential growth and this one's exponential decay. So take a minute, look at this example here and see if you can pause the video and answer this question. Looking at these functions below here, can you tell me which ones are increasing and which ones are decreasing? Another way to say that is which ones represent exponential growth and which ones represent exponential decay. All right, so all you had to do to tell this was look at the base on the exponent. Remember, if b was larger than 1, we got growth. All right, so a represents growth in this case because it's 3. All right, it's larger than 1, so it's growth. Here our base is 12. Well, that's definitely larger than 1, so we get growth again. In these two examples here, we have the bases both being fractions, so they would represent decay, right? Just like we saw when we graphed it on Desmos. All right, so let's continue our talk about exponential functions and mapping statements. All right, so we discovered that, as a changes, it changes the y-intercept. All right, so we can look at this function, all right, and because the y-intercept changed from 0, 0, 1 to 0, 4, it looks like we multiplied the y value by 4. Our horizontal asymptote did not change. So I can tell here that all I did to this function was change the a value from 1 to 4. Right? That would be the graph y equals 4 times 2 to the x. In general, our y-intercept is always 0, comma, whatever the a is. Whatever the a is. So if the question was, what's the a value of this dark red function? Here would be 4. You can see the y-intercept at 4. All right, so let's talk about performing a vertical translation. Right, that's just a type of transformation where we're moving the graph up and down. All right, so when we translate, right, a parent function, if we add a number to the end, like this, if we take the function and add some number to it, it's going to move that parent function up by whatever that number is. If we take that function and subtract a number from it, then it's going to move it down by whatever that number is. Remember, when I add or subtract a number at the end of a function, we call that adding a number outside the argument. And when we add or subtract a number outside the argument, that performs our vertical translation. All right, so let's practice that a little bit. Let's check that out, all right? If we want to, we can check it out on Desmos. Why not? That might be a good idea. So let's do that. So we kind of already saw here. I'm going to delete that black function here. I'm going to go ahead and we're going to um, fix A at +2, or we're going to fix A at B at 2, and we're going to let A change. All right, so I'm going to go ahead and add a number outside the end. So if I want to add a number outside the argument, I can say plus K out here at the end. I can add a slider. I'm going to fix A and B, so we're going to fix those both to be 2. So notice that our y-intercept is at, normally it's at 0, right? It's at 0A, but let's talk about, and we'll look at what happens when we go ahead and throw that K in there. Now it's at 0.3. We'll talk a little bit more about that in a second. It's like we added the K value to A. And in fact, you'll see that in your projects, right? When you're doing this project, that y-intercept, that initial value is your A plus your K. All right, and in this case, notice A is 2. So that's a 2 right there, and the K is 1. And now our new y-intercept is at 0.3. Look what happens if I shift K up. Okay, so notice what happened to the graph. I'm going to go ahead and just play, and I'm going to add K at the end here. So here, remember, we're adding or subtracting a number outside the argument. Notice the shape of the graph isn't changing at all, but it is shifting up and down. So you can see that vertical translation happening. It's moving it up as K gets higher, and as K becomes a negative, it's shifting it down. You can also examine what's happening to the y-intercept. All right, so the y-intercept, when I have K at 3.7, you take 3.7 and you add it to our A value, which is 2 here. So this should be at 5.7. So if I go ahead and click there, we can see that the y-intercept is now at 0, 5.7. Right, we have to add that vertical translation to our y-intercept because it shifted the whole graph up. I can tell when I've done a vertical translation because the horizontal asymptote also changes. So let's go ahead and make it a number like 2. Now notice here, if I zoom in, that vertical, or excuse me, the horizontal asymptote is occurring at whatever K is. And K happens to be 2. That means we're approaching 2, right? But we're never going to cross it. All right, and that's kind of how you can tell if you've taken a parent function and you've shifted it up or down, done a vertical translation. 1, you'll notice that the y-intercept should change. And 2, not more than that, look at the horizontal asymptote. See if that's been shifted as well. That's how you can tell if you've done a vertical translation. All right, so take a look at this graph. Let's go ahead and practice. So assume this is our parent function here. P of x equals 2 to the x. And we call P of x, remember, is the pre-image. What is the transformation of image I of x? So here's I of x now. What did we do? Let's write the mapping statement. So what did I have to do to transform P of x into I of x? Okay, so one of the things I look at is the horizontal asymptote. Did it change? Yes, it changed. And so did the y-intercept. So now I know that I performed a vertical transformation on this thing, right? A vertical translation. I've just shifted it, in this case, up. And the easiest point to examine, of course, is the y-intercept and see how it changed. Right, so here we can see that it changed from 1 to 3. So that means I had to move it up 2 times. So we write the mapping statement to get from P of x to I of x. P of x is map to, that's what that arrow means, is map to. We take P of x and just add 2 to it, and then we would get I of x. So that's a definition of I of x using a mapping statement. So take a moment to pause the video and tell me, how can we get, what's the mapping statement to get to h of x? Remember, we're starting with P of x and we're mapping this thing to h of x. So what would be the mapping statement? Well, I can see here that a vertical translation has happened. I'm looking at the y-intercept and I see that it's shifted down 1, 2, 3, 4 times. All right, so the new mapping statement is P of x is mapped to the arrow P of x minus 4. All right, so consider the function here. F of x is equal to 5 raised to the x. It undergoes a transformation. What is the correct mapping statement? So the preimage is labeled f. So that's the green one in this picture. So we're going to map f to g. So go ahead and write that mapping statement to map f to g. All right, so you should have just said that all we did is shifted up 1. Remember, look here. Look at the y-intercept to gain that information. I noticed that the horizontal asymptote changed, so that's how I know a vertical translation happened. And then I look at the y-intercept and see what that change was. In this case, look, we just shifted it up 1 to get from the green to the blue. So it was our original function plus 1. All right, so let's practice another one. Can you map the green one to the blue one? All right, so again, you can see that all we did to get from the green one to the blue one is shift the entire function down 1, 2, 3, 4 times. So it's f of x minus 4. Notice I'm counting how to get from one to the other. I'm not looking at the y-intercept itself. I'm not looking at that value, or else I would have wrote negative 3, right, which would have been wrong. We actually had to shift this thing down 4. All right, so we've talked about the vertical translations. Now let's talk about a horizontal translation. So when you take a function and inside the parentheses here, you add or subtract a number, that moves our function left or right. And it's kind of opposite of what you think. So if I'm adding a number inside that argument, that actually moves our function to the left by whatever that number is. Now if I'm subtracting a number inside the argument, that actually moves the function to the right by whatever that number is. So recall that when I'm replacing the x values with something in parentheses like we're doing here, and we're adding or subtracting a number in there, we call that adding a number inside the argument. So is what that means, if I actually had the function of something, everywhere I saw an x, I would replace it with the quantity x plus some number or x minus some number. That does our horizontal shifting. All right, so let's go ahead and check that out on Desmos. We can do it the same way we did sort of for the vertical translation. So now I'm going to go back to Desmos here, and I'm going to change our definition. And instead of going in there where they have the x, I'm going to go ahead and in our base function here, I'm going to write x. I'm going to define it to be our value function here. I'm going to keep those sliders the same, except for this one. Then I'm going to go ahead here and I'm going to define a new function. I'm going to call this one, the original one, I'm going to call it f of x, just so I can write it the same way that we did before. I'm going to call this new function g of x. And I'm going to say that it really is f of x, except for I'm going to perform that horizontal transformation. So I'm going to add that number there. So we're going to call that h. Okay, so now is what I've said here is this new function g of x is f of x, but I'm inside the argument where the x is, I'm going to replace it with x plus or minus whatever I let h be. And here I can let it be anything. I'm going to change the color so we can tell the difference between the two. So we'll make it green, maybe darker, black. All right, so let's go ahead and play with that a little bit. Let's see what happens as I go ahead and change the value for h. So right now in our function, the h should be 0, and that would map it right on top of the other, our red function, right? Right when it's at 1, rather. There it is. So there's h is 0. So this would perform no shift, right? And you can see that it's right on top of our function here, our red function. Okay, so now let's let h be a positive number. So according to what I just told you, right, adding a number inside there. So if I let it be a positive, like say +2, it should actually shift the graph to the left 2 units. Let's see that happen. There, so now I've changed the value of h to 2. And then notice what happened to these coordinates here. I'm going to go ahead and there's our y-intercept at 0, 2. And now this point has been shifted to the left by 2 units. There's our new point right there at -2, 2. All right, so we left the y value the same, but it was the x coordinate that changed by 2. All right, so that's what a horizontal shift does. All the y values of every point is going to stay the same. The x values are going to be changed by whatever that h is. So if we're adding a number, it shifts it to the left. Remember, and subtracting a number will shift it to the right. So let's see this minus the number, like a -2 here. Notice how I'm shifting the graph now to the right. Let's go ahead and let this animation play so you can actually observe the transformation yourself. That's pretty interesting. One thing I notice, well, I notice a couple things, but one thing I still notice is that notice that horizontal asymptote is not changing. It still remains at 0. Okay, so performing a left or right shift does not change our horizontal asymptotes. But notice that in fact does change our y-intercept. Right? It changes our y-intercept because we're moving the graph, we're shifting this whole function here to the left or to the right, which is changing our y-intercept. Now, the way that you could tell if you're doing a horizontal transformation, right, or translation versus a vertical, is you can compare the points. Right, so that when you have this on your problems, you'll compare the points, and when you're doing a horizontal transformation, you'll notice that the y coordinates don't change, but the x coordinates do. And it's the opposite when you're doing the vertical. That's why they'll always give you points to compare in your checkpoints and in your exams. So you can actually tell which one we did. All right, so let's take a look at these functions here. Here's our pre-image, p of x. Can you write the mapping statement that will produce I of x? And then write the mapping statement that will produce h of x? All right, so you should be noticing here's what I'm looking at is here's where this point is. I identify a point, and then usually I start with the one that's the pre-image. It's y-intercept, and I see how I shifted it right to our new point here. So it looks like we took this one, and remember we shifted it to the left, so it's p of x is mapped to p of the quantity x plus 3, right? That's not a mistake. Adding shifts to the left. So what do you think it's going to be for h of x then? All right, so if you said that h of x is p of x with the parentheses x minus 5, you're correct, because we shifted it to the right 5 units. So I would change the argument to x minus 5 to get from p of x to h of x. All right, so consider this parent function here. Let's see if you can go ahead and pause the video and write the mapping statement that will map f, the green function here, to g, the blue one. All right, so take a look at a point that you can identify and see how the x coordinate has changed. All right, so you should have said that f of x is mapped to f of the quantity x plus 3. That's our mapping statement. All right, so it's just telling us that, hey, we took the green one and we shifted it to the left 3 units. And there you can see that we did 1, 2, 3 to get our new point. All right, let's consider this decay function here. What is the mapping statement that will map f to g? That's right. It's f of x is mapped to f of the quantity x minus 3 because we shifted it to the right 3. 1, 2, 3. All right, so that concludes this lesson on exponential transformations. Make sure you complete the asynchronous session.